The sample space, denoted by omega, is the set of all distinct, elementary outcomes of a random experiment. It represents the substrate of possibility, the exhaustive list of every conceivable future state or resolution of reality under observation. In the triplet, omega, F, P, omega is the domain. It is the set of noumena, things as they are in themselves, before they are filtered through the lens of observation. Formally, omega is a non-empty set containing elements omega, referred to as sample points. The definition imposes two critical constraints on these points. Exhaustiveness. The set must cover every possible outcome. No experimental result can occur that is not represented by an omega in omega. Exclusivity. The outcomes must be mutually exclusive. If the experiment concludes, exactly one omega has realized. While introductory texts often trivialize omega as a finite list, e.g., outcomes of a die roll, in rigorous analysis, omega is an object of immense potential complexity. It serves as the ambient space for the theory. 2.2 Complexity classes of omega. The mathematical treatment of the sample space bifurcates based on its cardinality and structure. This distinction dictates whether we can define probability via simple summation or if we require the heavy machinery of measure theory. 2.2.1 Discrete sample spaces. When omega is finite, e.g., card shuffling, or countably infinite, e.g., the number of coin flips until a heads appears, omega equals n, the structure is relatively transparent. In these cases, the size of sets can be determined by summing the probability mass of individual atoms. Singletons. Here, the sigma-algebra is typically the power set P of omega, meaning every conceivable subset of outcomes is a valid event. Uncountable sample spaces and pathologies. The necessity of the complex machinery we will discuss later, F and Borel sets, arises when omega is uncountable. Consider omega equals the interval 0 to 1, representing the selection of a random real number. If we assume a uniform probability distribution, the probability of any single outcome omega is necessarily 0. If it were any epsilon greater than 0, the sum of probabilities would diverge to infinity, violating the axiom that probability of omega equals 1. Consequently, in uncountable spaces, probability is not a property of points, but of sets of points, or intervals. This shift from point logic to set logic introduces the measure problem. We cannot simply assign a measure to every subset of R without encountering logical contradictions, such as the Vitali set. Thus, for uncountable omega, we must restrict our attention to a specific collection of measurable sets, motivating the introduction of F. 2.3 Omega in stochastic processes. The space of trajectories. In the advanced context of stochastic calculus, omega takes on a richer form. For a stochastic process such as Brownian motion Bt of omega, the outcome omega is not a number, but a function. Here, omega is the set of continuous functions. When we perform an experiment, we are effectively selecting one timeline from the bundle of all possible timelines. Visualizing high-dimensional omega. If we model a sequence of infinite coin tosses, omega is the space of all infinite binary sequences, which is topologically isomorphic to the Cantor set. The God's eye view. Omega represents the view of an omniscient observer who sees the entire realized path of a process. The role of the sigma-algebra, as we will see, is to represent the view of a mortal observer who only sees the path unfolding over time. The sigma-algebra F, the structure of information. If omega represents what can happen, the sigma-algebra F, or sigma field, represents what can be asked. (3.1) Axiomatic definition and structural properties. A collection F of subsets of omega is defined as a sigma-algebra if it satisfies three specific axioms that ensure stability under standard logical operations. Axiom 2. Closure under complementation. If A is in F, then a complement is in F. Implication. If we can determine the probability that an event did occur, we must logically be able to determine the probability that it did not occur. Axiom 3. Closure under countable unions. If A1, A2, and so on are in F, then their infinite union is in F. Implication. This property, known as sigma additivity, distinguishes a sigma algebra from a simple field which is only closed under finite unions. This is crucial for limit theorems in calculus, such as the law of large numbers, where we deal with sequences of events n to infinity. From these axioms, De Morgan's laws imply that F is also closed under countable intersections. This symmetry ensures that the logical connectives n, or, and not are universally valid within the system. 3.2 Visualizing F as information resolution. One of the most profound pedagogical insights in modern probability is the interpretation of the sigma-algebra as a measure of information resolution or pixelation. Consider an observer viewing a high-resolution digital image omega. Omega, the reality, the continuous, infinitely detailed scene. F, the observation, the grid of pixels available to the observer. If F is the power set P of omega, the observer sees the image with perfect clarity. Every point is distinguishable. If F is the trivial sigma algebra, the observer sees only a single average color. They know the image exists, but can distinguish no features within it. A sub-sigma algebra G subset F represents a coarser resolution, larger pixels. If we refine G by adding more sets, splitting pixels, we are increasing the resolution of our observation tool. 3.2.2 The tickets in a box analogy. To understand measurability, imagine a lottery where a ticket is drawn. The outcome omega is the specific ticket. The ticket contains all attributes of the outcome: color, number, suit, texture. F, a rulebook of questions you are allowed to ask the game master. If the event A equals all red tickets is in F, you can ask is the ticket red? And receive a definitive yes or no. If the event B equals all textured tickets is not in F, the question is the ticket textured? Is meaningless in this system. The information is opaque to you. This analogy is fundamental to understanding conditional expectation E of X given F. The conditional expectation is the best guess of a random variable X given the resolution limits of F. If F is coarse, our best guess is a broad average. If F is fine, our guess approaches the true value of X. 3.3 The paradox of information. Dubra and Eshenique. While intuition suggests that more information, a finer partition of omega, is always better, rigorous analysis of sigma algebras in decision theory reveals complexities. A signal partition generates a sigma algebra. However, finer partitions do not always generate finer sigma algebras in pathological cases, leading to situations where a decision maker might theoretically prefer less information if the sigma algebra generated by the finer partition fails to include specific critical events due to measurability issues. Specifically, Dubra and Eshenique demonstrated that if information is modeled by partitions, a finer partition tau implies more information than tau prime. However, the sigma algebras generated by these partitions might not strictly follow the inclusion in specific infinite settings. This highlights the importance of defining information strictly via the sigma algebra rather than the heuristic partition of the sample space.